Okay, so last time. Right, well, last time we had fun talking about degrees. So in particular, we established that if you have a map with and a point with f inverse of y finite, then then the degree of f can be computed from the local degrees. Okay, and we saw that this extends to compact, connected, oriented manifolds. Right? Both the fact that there is a degree and that you can compute it using the local degrees whenever you have a point with finitely many inverse images. And we talked about how if everybody's smooth, meaning the manifolds and the map are smooth, then almost all y's have this property. Right? And so in practice, in real life, that's how you compute the degree. Okay. So that was last time. Questions on last time?
Can you say one more time how you get the local?
Sure. So every point xi has a neighborhood in Sn that looks like Rn, right? Is homeomorphic to Rn, right? So f restricts to a map between such a neighborhood of xi and such a neighborhood of y. And so you look at the induced map in local homology of these neighborhoods. And you are again mapping z to z. And so it's just multiplication by some number, and that's the local degree. Right? Yes?
When you say this extends, you mean this property extends if we don't have a map between the sphere and the sphere? If we have a map between compact connected?
Oriented manifolds, that's correct.
Okay.
Yeah, so yes, so we saw last time, I claimed last time, that if you have compact connected oriented manifolds, then the top homology group is just the integers. Right? And so it makes sense to talk about the degree. Yes?
Will Hadrian be here to collect your homework on Thursday?
That's an excellent question. I will look into it.
Okay.
Yes, more questions? Okay, so we want to use the degree a little bit in disguise, but we'll see that that's what we're doing, to define a homology or a way of computing homology that works for cell complexes. Right? So at the moment, we know how to compute. So if X is a delta complex, then we have a special way of computing the homology that gives us the same answer as the usual way of computing homology. Right? So singular homology, this is defined for any space. This requires a delta complex structure. So this one is easy to compute. This one is easy to prove theorems about. So it's nice to do the same. But delta complexes are very special. What you have a lot of are cell complexes. So we want a similarly easy way of computing the homology when X is just a cell complex. So remember that cell complexes are also known as CW complexes. So we're going to define a chain complex. And what we want is for the nth one to be a free abelian group on the n cells of X. Right? So mimicking what we did when we have a delta complex, we're going to take the free abelian group on the n cells. And then, if you recall, the reason that we liked delta complexes is that then we knew how to define the boundary map. Right? So we had a nice orientation on the regular simplex, the standard simplex, and so we used that to get a boundary map. So the reason we didn't start with cell complexes is that we didn't have a way of defining the boundary map. So the claim is that now we can define the boundary map. Okay? So well, let's work up to the definition of the boundary map. So we want to define. Okay, so here's another way of thinking about the n cells of X. So if X is a cell complex, then first of all, if you look at the n skeleton relative to the n-1 skeleton, then this is either the free abelian group on the n cells if n is equal to k, or just 0. Right? So we saw this for delta complexes, but in fact it's true for cell complexes. It's also easy to prove that if you look at just the n skeleton, then this is 0 if k is greater than n. And on the other hand, if you look at the inclusion of the n skeleton, then this induces an isomorphism in homology if k is less than n. Okay? So none of these should be surprising because we already had this for delta complexes. It's just that it's going to be true for arbitrary cell complexes.
What exactly is X to the n mean here?
This is the n skeleton. So remember, a cell complex is a space built up inductively by attaching cells. Right? You start out with a bunch of points, and that's called the zero skeleton. Then you attach one simplices, or intervals, by deciding where you're going to map their boundaries. Right? And so once you've done that, what you have is called the one skeleton. Right?
Okay. And then my other question is there a cell complex that we've seen so far that we wouldn't be able to turn into a delta complex? Because I feel like everything so far we have been able to.
So that's a fair question. And I don't know off the top of my head.
Okay.
But the thing is that you don't want to have to turn it into a delta complex. It's like we had some exercises where it was, here, take this space and show that it admits a delta complex structure. So usually it already had a cell complex structure, and then you were doing some subdivisions until you had a delta complex structure. We want to not to have to subdivide, right? Okay, more questions on the statement? Okay, so the proof of A is the same proof as for delta complex structures, namely that this is a good pair. So hk of xn minus 1 is the same as hk tilde of xn over xn minus 1, which is hk tilde of a wedge of n spheres which is the direct sum of these guys, which is the direct sum of z's if k is equal to n and 0 else. Okay, on the other hand, for B and C, we look at the long exact sequence of the pair. Right, so okay, so we have hk xn minus 1. Okay, so if k and k minus 1 are different from n, then this is 0 and this is 0. So we get that hk minus 1 of xn minus 1 is the same as hk minus 1 of xn. So if k is greater than n, so let's say if k minus 1 is greater than n, then so then k and k minus 1 are not n, and so hk minus 1 of xn is equal to 0. Which is what we wanted to prove, except that I put k minus 1s here when I should have put k for this to look nicer. Okay. So that takes care of B. On the other hand, if if k is less than n, then what I want to do is let it grow. So we have hk of xn is the same as hk of xn plus 1. Hk of xn plus m for any m. Right, so if instead of moving the k, just move the skeleton you're looking at, all of these are isomorphic. Okay, so we have two cases. Either x is finite dimensional or not. Right? If it's finite dimensional, then we're done. You just take large enough m, and then you get all of x. Right, so this proves C. Okay, so if x is infinite dimensional, well, we've had to handle infinite dimensional cell complexes a couple of times before, and we always do the same thing. We take advantage of the fact that any compact subset of a cell complex intersects finitely many cells, right? So that means that if you look at things at the chain level, then for each individual chain, it's enough to have this statement for finite dimensional chain complexes. So to be more specific, let's give this a name. Let's call this I. So let's check that I star is surjective. So given a class in HK of X, we can represent it as well, with a finite linear combination of singular n simplices, k simplices, each one has image that intersects finitely many, well, let's just say that intersects contained in some skeleton. Let's just say it like that. Right. Each one has image contained in the L skeleton for some L. And since there are only finitely many, I can pick L large enough so that the L skeleton contains all of the images. Okay, and then we know that, that HKXN surjects, well, in fact, is isomorphic to HK of XL. Right, so that particular class is actually present here, and so it's in the image of I star.
That says there exists L greater than 0?
Sufficiently large, so much greater than 0. Mm-hmm. Okay, and to see that it's injective is similar. So if I star of a class is equal to 0, that means that that class is so any representative say C is a boundary in K of X. Perhaps I have too many Z's. Let's go with Z. Is a boundary in here, right? But, so say C is equal to boundary B. But this B is a finite linear combination over the integers of singular k plus 1 simplices. And so it has image contained entirely in a finite skeleton of X. So we can find XL, L sufficiently large, such that the image of the singular simplices with non-zero coefficient in B is contained in XL. Okay. And then since we know that mapping xn to xl is injective for L greater than n, we know that actually this class was already 0 in HKXN. Okay. So it's our usual, really our unique trick for dealing with infinite dimensional cell complexes, right? That every element only involves a finite skeleton. A finite dimensional, yes.
Can I ask a question about the proof of B?
Sure.
Really, it's just the last line. I don't see how it follows from the line before. So I get that for k and k-1 not equal to n, you have this isomorphism from the long exact sequence. Why does that imply that the k-1 homology next to the 0?
By induction, I suppose. I didn't say much, did I? Yeah, by induction. So you just keep going down until you get to k minus 1 of x0. Right? And then that one is identically 0. Because you just have points. And so then we know what the singular homology is. Yes, thank you. I should have said that. More questions? Okay. Okay, wonderful. So after this preliminary, now let's talk about how you would put a boundary map to turn these groups into a chain complex. Right, so we have C n plus 1, CW, and I want the boundary map to get to Cn, CW. So what we do is we identify with this. Right, so this is H n plus 1 of x n plus 1 xn. Okay, and then singular homology has a boundary map. So this would be the connecting map in the appropriate long exact sequence. And that'll bring you down to xn. And then you just include that in hn of in its long exact sequence. And that's that one. Right? So this is denoted like this. Okay, so notice there are two. So I have this pair and I have this pair, and each one of those pairs has a long exact sequence, right? So this is the boundary map from the long exact sequence of this pair, and this is the inclusion from the long exact sequence of this pair, right? So it's because they come from two different long exact sequences, it's not automatic that their composition will be 0. Right? Which is why this is potentially interesting map and not identically 0. So this comes from long stack sequence of this pair, and this from long stack sequence of this pair. Okay, that's also how we can see that, well, I'll leave that up. So I'll leave here, this is Hn of Xn. So why does this square to 0? So let's say you have Cn plus 1. We're going to map to Cn and then Cn minus 1. Okay, so this is Hn plus 1. Xn plus 1, Xn. This is going to map to H, N, X, N, and then J, H, N, X, and Xn minus 1, and then Hn minus 1, Xn minus 1. And then Hn minus 1, Xn minus 1, Xn minus 2. Okay, let's make this match up. Okay, so the point is that these are both from the long stack sequence of Xn minus 1. Right? And if you compose two consecutive maps in the long stack sequence, you get 0. Okay. Okay, so we wanted to do two things with this. We have a homology, so this squares to 0, so we have a homology. And we want to know that this homology is the same as the singular homology of X. Right? In particular, this will show that it doesn't matter what cell complex structure you put on X. You always get the same homology. And then I said that this had something to do with degree, so we want to relate this with the degree of some map. Okay, so I think right away I want the theorem. That this, so the inclusion induces an isomorphism of homology. Okay, so as you'd expect, this is just going to be fun with the long exact sequence of pairs. So let's look at the relevant piece. Let's put hn plus 1 of xn plus 1 xn. Let's give ourselves more space. Okay, so here, let's map up to, so with the boundary, we get h of xn, and then this further maps to h n of xn plus 1, and we've already seen that that is hn of x. And then that goes to 0. And this comes from h n plus 1 of xn plus 1. And then before that, it would be h n plus 1 of xn, which is 0. So here we have from the long exact sequence of this pair, right? This is the piece of it that includes this, right? It has a 0 on one end and a 0 at the other end, right? If you were to keep going, then you get these isomorphisms that we saw in the previous theorem, lemma.
That second class map is just the inclusion map, right?
This is just the inclusion map. That's right. Okay. Now, this maps forward to hn xn xn minus 1. And this one we know is the composition of taking this boundary from this long exact sequence and then taking the inclusion from the long exact sequence of this pair. Right? So that means that we have over here the long exact sequence of this pair. And of course, this guy has its own long exact sequence. And this composition, is the boundary, is the CW boundary map. So this would be n plus 1, n plus 1, and so on. Right, and this. Yeah. Okay, so every one of these sits inside a long exact sequence, and those fit together with these common groups to give us this diagram. Okay.
How did you come up with this?
Well, so somehow this equality is natural, right? Okay. So then you need a map that goes from here to here, right? So I think, on a good day with some staring, you would have come up with this boundary map, right? And then once you've come up with this boundary map by combining the sequences, well, then you just get carried away. And you just draw all of the sequences, yeah. And that's your diagram. OK, but the nice thing is that now that you have this diagram, you just do some staring. and you get this there. OK, so why? OK, so here is the staring to look at. So Hn of x is, okay, well, yeah, Hn of x is right here. Right? So that means that it is, and then since I have a 0 here, that means that this guy is surjective, right? And so it's going to be, this guy is isomorphic to the image, sorry, to this guy modulo the kernel of this map, right? But because this is a exact sequence, the kernel of this map is the image of this map, right? So here we get that this is Hn of xn modulo the image of boundary n plus 1. Okay, great. So I have here and some subgroup that I'm modding out by. And now this guy is injective, right? Because I have a 0 over here, right? So I can take this subgroup over here and I can move it over here. Right? So J star injective tells us that the image of this guy is the same as the image of this map because this commutes. Well, they're isomorphic. They're not the same because they live in different groups. On the other hand, the image of Jn star is Hn xn, which is the kernel here we're using that Jn minus 1 is injective. Okay, so we want to know what's the kernel here. Hn, xn. Yeah. Right? So the image of Jn, so I should put an n. The image this way is the kernel of this map. And we identify it with the kernel of this map because this guy is injective. Okay. But then the kernel over the image gets mapped by Jn to Hn xn over the image of the boundary map here, and that is Hn of x. Okay, so the isomorphism between these guys really is just inspired staring at that diagram. Yes?
Sorry, I can't see
So
the map between
J and star.
J and something. Yes.
Mm-hmm. Right. And it's an isomorphism because we've modded out by the kernel. Okay. Okay, wonderful. So it does what we want. It computes the homology, and it only uses the cell complex structure, right? Now, in practice, that's not how you would compute this boundary map, right? In practice, you want something just like the delta complex structure. You'd like to be able to just stare at it and decide what the boundary map is. Okay, so that's where the degree comes in. So if we just have C n plus 1 CWX so here, this is the free abelian group on the n plus 1 cells. So let's say you were to take an n plus 1 cell, and then this takes it to the free abelian group on the n cells. So whatever this is, it's going to have to look something like this. Right? So it's just some z linear combination of the n cells, right? Because everything in here looks like this. Right? So it's just, what are these coefficients? So what we're going to show is that, so claim d alpha beta is the degree of, I think I want to call this delta alpha beta. Okay, so this is an n plus 1 cell. So that means that it's just a disk, an n plus 1 disk, that we're attaching to the n skeleton of X by means of some attaching map defined on its boundary. Right? So, okay, look at the boundary. Let's put an alpha. And attach that onto X. And I want to relate this to the beta n cell. Right? So this is an Sn. So we're going to map it to an Sn beta, where we collapse everything outside of the n cell. So this is going to be the collapsing Q beta is collapse X minus the n cell, right? So every n cell is an n-dimensional disk that we're attaching by doing something on the boundary, right? So if you collapse everything in X except this disk, then all you're left with is this disk with its boundary collapsed, right? And if you have an n disk and you collapse the boundary, you end up with the n sphere. Right? So we have a map from the n sphere to the n sphere, so it has a degree, right? The claim is that that degree is this coefficient. Okay, so this is a purely geometric description of this boundary map. Right? So of course, why didn't we just do this? Because how do you know that this squares to 0? Right? Well, you could play with degrees and see that it squares to 0. But instead, we're just going to show that it's equal to this one, and this one was obviously squaring to 0. Okay?
Did you say what
Yes.
the phi alpha map was?
Oh, this is just the attaching map of the cell. Yeah. Okay, so this is called the cellular boundary formula for obvious reasons. So, again, we just have to draw the right diagram and then stare at it. Right? So in this case, the diagram is going to be like this. We're going to have So capital phi alpha is going to be the attaching map of the n cell. So this is just going to be E n alpha. So remember that when you have a cell complex, you have a characteristic map and an attaching map. So the attaching map is on the boundary, and the characteristic map is just an extension of that to the rest of the disk. Right? So this capital phi restricts to the boundary to be lowercase phi. So that maps you into hn, xn, xn minus 1. Oh, my indices have changed. Okay, n plus 1, n plus 1, n plus 1, plus 1, plus 1, n. Okay. So now this has a boundary map to hn tilde of boundary n plus 1 alpha. And on the boundary, capital phi alpha is just lowercase phi. So we end up with hn tilde of xn, and that's what you go with the boundary here. And this includes into hn minus 1, no, n, xn, xn minus 1, so that there is the CW boundary map. Okay, now here we have this map, capital delta, mapping into hn tilde of Sn beta. Here we have a collapse mapping into hn tilde of x n over xn minus 1. And here we have an isomorphism n over xn is 2, n minus 1 over n minus 2. Okay, so this is an isomorphism we saw a long time ago. Yeah, I think we saw it when we were talking about excision. Okay, so, and this map, obviously, is what happens when you collapse the n minus 1 skeleton in xn, right? But over here, we needed to collapse everything, not just the n minus 1 skeleton, but everything except this n cell, right? So this one is when you collapse what's left except for that n cell, right? So you collapse all of the other n cells. Okay, so this, as we know, is just a bouquet of spheres of the appropriate dimension given by the n cells. And this is just a projection onto the beta factor in that bouquet of spheres. Okay, so wonderful. We have a generator here. So the class of the disk generates here. And so let's just follow this guy around the diagram. Right, so let's fix that. So when you map it into here, you get the class of E alpha n plus 1. And then when you hit it with the boundary map, you get the sum of d alpha betas E n beta. When you map this guy this way, you get the degree of delta alpha beta, right? Because this is exactly this map. This is the induced map. And it's given by multiplication by the degree, right? And this was a generator, so we just have multiplication by the degree times 1. On the other hand, if you start with this guy and you go around the diagram this way, right, then like we said, this one is just a projection onto the betath factor. So you just get d alpha beta. Right? And since the diagram commutes, those are equal. Okay. Excellent. So the point is that the degree is something very geometric, but also has a very natural relation with homology, right? It's just what you multiply the generator by when you're mapping between homology of spheres. And the cell complex is built up from its different cells. So we can just see what happens when you attach a cell and find that this coefficient is given by the degree. OK, so wonderful. In practice, this is how you compute what the differential is, as we'll see in some examples. OK, so let's do a two-hole torus. So we know what the identification space for this is, right? So it's just an octagon. And the word around it is just the product of the commutators of AB and CD. And let's call the interior U. Right. So this has a cell complex structure with 1 2-cell, 4 1-cells, and a single 0-cell. Right? And as we've seen before, you could subdivide this and get a delta complex structure, right? But the point is that now you don't have to. Right? OK. The one skeleton is just a bouquet of 4 circles, 1 for A, 1 for B, 1 for C, 1 for D. OK, and so our complex looks like this. Where this is just a copy of Z, this is just a copy of C's fourth, and this a copy of Z. Right, and we want to know what are the boundary maps. OK, so the boundary map on 1-cells, this behaves just like the boundary map on 1-cells for delta complexes. So it's just the difference of the endpoints. And since all of them are 0, all of them are the same endpoint, this is just 0. OK. This guy, it turns out, is also 0. Okay? So why is that? So if we write this is the sum of d alpha e alpha, where alpha runs over the ABCD, right? Then let's see, the dA would be the degree of the map from the circle to the one skeleton given by this word. Right, so boundary of U to the loop A. OK, so remember what you do is you take U, you include it in, right, the boundary of U, you include it in, so that's this word, and then you collapse everything in X except the cell you're looking at, right? So we're looking at A, right? So we collapse everything here except A, right? And then we see what degree we have, right? Well, what is this word going around? If you ignore everything except A, it's A and then A inverse, right? So this is the degree of A followed by A inverse, and that's 0. Gesundheit. Right, because you cover every point twice, but going the opposite directions, right? So the degree is just 0. And it's the same for any one of those one cells. So both boundary maps are identically 0. So that's ideal for computing cohomology, homology. So it follows that the homology, that's what was CW homology, is the same as the corresponding chain group, right? Because all of the boundary maps are 0. So this is just Z if n is equal to 0 or 2, C to the 4th if n is equal to 1, and 0 else. Right. The exact same thing works for arbitrary genus. So the same proof. Well, same ideas work for. No, I don't need 2GS. MG. Here, the identification space is some polygon with a bunch of sides with the word around it, the word around U is just a product of commutators, say A1, B1 times A2, B2, AG, BG. Right? And so when you compute the boundary map in degree 2, you get 0 for the same reason that each coefficient, dAi, say, is the degree of the attaching map from the boundary to the loop with just that AI. And this is the degree of AI followed by AI inverse. Because all you do is you look at this word and then you ignore everybody except for AI. And it occurs twice with opposite signs. Right? So we conclude that the homology of MG is Z in degrees 0 or 2, C to the 2G if n is equal to 1 and 0 else. So much simpler than anything we had before to compute this homology. And also very geometric. Okay. Yes?
So let's say we had a cell complex where, like, say, the A edge is pointing the same direction each time.
Let's.
So how then, like, how do we know which orientation we're supposed to view that in? That is to say, how do we know whether the boundary map gives us 2A or negative 2A?
Well, you have an orientation. Well, I mean, every cell you could have an orientation, and so you have an attaching map. It is an actual map from the circle, and so the circle has an orientation.
So basically, it depends on whether we're attaching U clockwise or counterclockwise.
Exactly, yeah.
Okay.
Okay, so let's consider exactly something like that. Let's say you have RP2. So let's say that you have A and A. Right. So again, we don't need to subdivide or anything as we would for a delta complex structure. This is a perfectly nice cell complex. Okay, so, and indeed in this case, the one skeleton is just a single loop with A, and the boundary map applied to U is going to be the degree of the map from the boundary map to here, which just does A twice. So it's going to be, it's going to be this times A. So it's just going to be 2A. Because you just go around the circle twice. So that has degree 2. Okay, so this is Z, this is Z, this is Z. This map is multiplication by 2, and this map is multiplication by 0. Right? So we see that H n of RP2, CW, but it's the same, is going to be Z in degree 0. It's going to be C mod 2Z in degree 1, and it's going to be 0 else. Right? Obviously, for degrees greater than 2, and for the degree 2, it's because I'm supposed to take the kernel modulo of the image, right? But this map doesn't have any kernel; it's injective.
So this, in addition to other things, tells us that RB2 isn't orientable.
That's correct. So once we've shown, it's probably the next semester, that orientable manifolds have topology equal to Z, then this shows that it's not.
So if we draw one of these pictures with, of a cell complex, is there a particular convention you want us to follow as to what the orientations of two cells are?
Well, if you have a
As long as you have the same
And simple.
orientation throughout, which you would say that's already.
yes,
I mean, yeah. I was
yeah.
wondering if,
In particular, in this case, if I had drawn the arrows, the identification of the A's in the opposite direction, in this particular case, it wouldn't have made any difference, right? Because I would just be multiplying by -2,
right.
and I would get the same groups,
Right.
right? But so, orientation is something that we've made sense of on standard n simplices, right? And I talked about what it is on a manifold, but this semester, unless we manage somehow to get to that, it shouldn't matter. It should always,
All right.
yeah. Okay, great. So let's keep going with projective spaces. So let's do RPN, which, as you know, is what you get from Sn if you identify each point with the antipodal point. Good. Okay, so let's write Qn as the quotient map from Sn to Rpn. And notice, so let's draw. For S2, if I look at the upper hemisphere and the lower hemisphere, then of course Q just identifies points in the upper one with the lower one, and then identifies antipodal points on the equator. The equator is a copy of S1, and if you're identifying antipodal points there, you're just getting RP1, right? So in general, you can always write Rpn as Q of, say, the upper hemisphere and an Rp n minus 1 from the equator. Okay, so using this and induction, you can show that Rpn has a cell complex structure with one cell in each dimension. The attaching map of, say, EK is S k minus 1 attaches to RP k minus 1, but that's just the collapse map. It coincides with Q k minus 1. Right? So when I'm attaching the K disk, I go up to the K minus 1 skeleton, and I need to attach the boundary to that. Right? But the K minus 1 skeleton gives me an RP K minus 1, and my attaching map is just the quotient map from here to there. So, so this delta, the map that we want to find the degree of, goes from Sk minus 1 to Rp k minus 1, and then collapses everything but the cell I'm looking at well, Q is perhaps not a good choice. P. Okay, so restricted to upper or lower hemisphere, delta is a homeomorphism. And these two homeomorphisms are related by the antipodal map. Right? So you're doing the same thing on the upper hemisphere as on the lower hemisphere, just at the opposite point. So that means that the degree Right, and remember that we computed the degree of the antipodal map is -1 to the k. So the degree of this is equal to, well, you have the local degree at one point and the local degree at the other point, and the difference between the degrees is just as -1 to the k. So this is equal to 0 if k is odd, and 2 if k is even. Okay, so that means that the CW complex for RPN looks a little different if n is even or if n is odd, right? So you always have a SED anywhere where it's not just, anywhere where you have cells, you just have a single cell. Okay, so this last map is always 0. The one before it is always 2. So what's different is just where did you stop. So if n is even, then you start out by multiplying by 2, whereas if n is odd, then you started out by a 0 map. So that means that hk of RPN is z if k is 0, and if k is n, if n is odd. It's z mod 2z for all k's in between that are odd, and it's 0 else. Right? So, and then looking ahead, so anticipating the theorem I mentioned about orientability, you can see that it's orientable if and only if n is odd.